All right. Good afternoon, everyone. So for today, we should be finishing off chapter 2. Oh, and I noticed at the end of last class and forgot to change it. There's a typo in the title. So it should be, do we trust the experimental results? And I don't know how it ended up the other way, because E and O are nowhere near each other on the keyboard, but that's what we were going for. So we had finished up talking about sort of the basics of designing and things to consider while running experimental research. And we had compared that experimental research to the descriptive research that we talked about beforehand. And so now we want to sort of continue on with our experimental, talk about what we think about our results. Some of this is going to be specific to experiments. Some of this is going to be general research. And then we're going to talk about some statistics, again, very vague terms. And as we go through, I'll kind of drop some hints as to what kind of information is important, as per usual. So the first of the things that we want to compare, and again, we have two similar terms on the same slide, which is usually a good indicator of them being associated in some way. So we have internal validity and external validity. So internal validity, it's defined as the degree to which results can be attributed to the independent variable and not other explanations, which is the fancy way of saying if we have high internal validity, we are very confident that the results that we're observing happen because of the manipulations that we did to our independent variable. However, if we have low internal validity, then we have other things, those confounded variables that might be floating around, something else might be driving that relationship. So if we quantify that internal validity, say it's really high, that means it was a good experiment, we think our results are accurate and they're telling us what we think they're telling us. If we say we have low internal validity, then that's really problematic because we got results, but we're not very confident in them. And that's troublesome if you want to start generalizing. So the other kind of validity that we really care about is external validity. And kind of when you have bad internal validity, you just stop there because you don't really know what's going on. But if you have good internal validity, then we can start making judgments about how far we can apply our results. So our definition is the degree to which results can be generalized to other people, across settings, and across time. So we've already kind of touched on this idea when we were talking about choosing a representative sample, and how if our sample was biased, it wasn't a good representation of the population. And if we had that biased sample, it wouldn't allow us to generalize our results from the sample to the population as a whole. So in that situation, a biased sample would be poor external validity because we can't apply back to the big picture. So that can be problematic if, say, we were only looking at Alberta University students versus students all across Canada or North America. And that can be like, you can do divisions based on locations or groups or periods in time or whatever. However you divide up and sample from your population of interest, there can be issues with where you can apply those results. And those are external validity issues. So for a good experiment that we can apply to other situations that we can generalize, we want high internal and external validity. Both are going to be important. But we talked about our situations where you can get away with having low external validity as long as you keep it in mind. So those were the things where we can get away with not having a representative sample. Those situations apply. All right, so next we're going to talk just, again, very briefly about statistics. And when we're talking about statistics, we're talking about using mathematics to organize, summarize, and interpret some kind of numerical data. So this is the stuff that we're measuring from our samples. So this would be our value for our independent and dependent variables, the things that we manipulate and measure. And so we can have two different broad categories of statistics. The first being descriptive statistics, which, as you might imagine, are used for describing or organizing and summarizing that data in some kind of useful way. So maybe if you're putting together a bunch of graphs, if you wanted to find out what the mean is of your data, or maybe we wanted to quantify how much spread or noise is in our data, that would be descriptive statistics. That's describing our data in some useful way. And for that, we see lots of graphs. And that's what we're going to be going through in this chapter. Lots and lots of graphs. What I typically do with graphs is I will show them to you and explain how they work. But because of the limitations of testing with images and how they don't always come out the same, say, clarity as you would like when you mass print, I typically don't use graphs or images on tests. So I wouldn't ask you to, say, interpret a graph or something. I just know that some people get nervous about that. But I've seen those memes about, like, a graph being perfectly clear on the teacher's copy and then it's completely illegible on the student's copy. I have been at the wrong end of that, so I don't do that. But yeah, just a disclaimer, because you're going to see a lot of graphs. So that's descriptive statistics. The next is inferential statistics. And this is actually what most people think of when they think of statistics, which is when you're trying to draw conclusions. So you interpret that data and use some kind of setup to figure out if you can conclude that there's a difference or not, or if you can conclude something significant or not. So inferential statistics is when you're making an inference or drawing a conclusion, and descriptive statistics is sort of putting that information together in a way that we can look at and sort of generally summarize. Okay, so we're going to start off mostly with our descriptive statistics, so the general ways to describe data. And hopefully this will be mostly review for you guys. So we'll start off with one of the easiest ones, and this is measures of central tendency. One of the easiest things that we can describe is where is the center of our data? Where's the middle? And there are three values that are typically used. We'll see the mean, median, and mode. Probably heard of those all through high school. So we have our graphs here. So the mode, I guess I should talk about the graphs first. Along the x-axis, our horizontal, that is going to be whatever value that we're looking at for our variable. So if we were looking at IQ, then that x-axis, that horizontal axis, would be IQ points. Then our vertical axis, our y-axis, on graphs like this, these are frequency distributions typically, sometimes density curves, which are almost the same. What those are telling us, that y-axis on the vertical, is how many people got that score. So a higher line or a higher curve at the top there means that more people got that score. And if it was a proper graph, we'd actually have numbers on those axes. These are just generic curves. But that's sort of what you should envision here. So with our mode, that's the most frequent value. So the mode occurs most often. So that is the highest point on that frequency curve. So that is right in the middle of the peak. Nice and easy to spot. We can also get our median. And the median is the one that occurs right in the middle. I remember this one because the median is the thing that runs down the center of a highway. So that's what the median is in our numbers. It's the number that's right in the middle, with 50% of the numbers on one side and 50% on the other. So to find the median, what you would do is organize all of your IQ scores or data values of whatever kind from smallest to largest, and you find the number in the middle. If you have an even number of numbers, so say you have 10 numbers, you can't find an exact middle, there are actually two, so you take the two middle numbers, add them together, and divide by 2. That's the typical way you do it. But if you have an odd number of numbers, then you just take the middle value, and that is your median. And then the mean is the last one, and this is the easiest, I think, to conceptualize, because this is what we've typically used all through high school. And this is the mean, which is just the average. So you add up all of the observed values that you have and divide by the total number of observations. So if we have 50 people, we have the IQ scores for 50 people, we'd add up all 50 scores and divide by 50 to get our average number. Now, what we might notice on here is that with this data, it kind of seems to lean to one side. So there's a tail trailing off in one direction. And the mean, median, and mode are all in slightly different places based on that sort of pull in one direction. So the mode is always going to be that highest peak. The mode is pretty resilient and not moved by extra stuff happening. And we'll talk a little bit about skew in a bit, but that just means that there's that mean in our data. So the mode isn't moved by it. The median is pretty resilient to it, but can shift just a little bit towards those extra outlying variables. So that tail that's pointing off to the right, that's pulling the median just a little bit to the right. And then our last value, the mean is very strongly influenced by outliers. So all of those extra numbers trailing off to the right have shifted our mean very far to the right. So if you have ideal data, which we'll talk about as being normal data, then our mean, median, and mode should all be about the same number. But in practicality, sometimes there are differences, and each of them gives us a different piece of information. So sometimes you'll actually see all three reported because they tell us about any kind of movement.
Where does the mean lie in this graph?
So that's the little triangle at the bottom. The blue triangle, that's pointing at it, yeah.
Like what's the rule that points?
So that's when you add up all your values together and divide by the number of observations, yeah. So that's what the rule is at. Yeah, I'm not sure why the other two got lines and this one didn't. It got an arrow. All right, so that was our where is the middle. Our next most common way to describe the data is to somehow describe the variability. And variability gives us an idea of how spread out our data is. So what is the shape of our data? So as I kind of just mentioned, that figure that we were looking at, that had some outliers. That had a little bit of skew. It was shifted to one side. So there were extra values on the right-hand side, which is actually a positive skew. But we can also get some quantifiable numbers. We can calculate things like range, which is where you look at the spread of your data. So subtract the lowest number from the highest number. So if our highest IQ score was 120 and our lowest was 80, our range is 40 IQ points. So there's a spread of 40 points between the lowest and the highest numbers. So the larger the range is, we know the more spread out our data is. We can also do things like calculate either standard deviation or variance, and these two are very, very closely related. And if you've done a stats course, you've probably done a lot of calculating standard deviation and variance, but we simplify it as it's the spread of the data around the mean. So it's a way of calculating. So we take our average point and we look at how far from the middle each and every score is. So the higher those numbers, the more spread in our data, kind of the fatter our curves get. So instead of having a nice clean curve, if we have a lot of variance or a lot of deviation, it gets wider and wider. If we have a very small variance or very small deviation, then our curve gets really skinny. And so we can actually see that on the next slide here. So this is another IQ score, and we're looking at division between men and women here. This is just theoretical data, not actual measurements, because you can see we don't even get an actual frequency measure on this, the y-axis. It just says general number of people-ish. So in our middle, we have an average of 100. And because our data is symmetrical here, because it's pretty darn close to normal, we're going to be seeing that the mean, median, and the mode are all going to be right around 100. And if you've actually studied IQ, this is part of how you construct IQ tests. They are intended to have an average of 100. So that makes sense here. But what we care about is both of our groups of data have the same mean, but they have different degrees of variance. So you'll notice that the purple curve, the men's scores, is a little bit wider. It means that it has more variance, there's more deviation from the mean, so it just means that the scores are further away or more spread out from the middle. And then in contrast, the women's score, the orange one, is the one on the inside. So it's a little bit tighter towards the center. So it means there's less variation, there's less deviation. And that's about as far as I go into standard deviation and variation, because we don't need it much more than that. All right, and then I've already talked about this, but this is specifically to show you how our skew can affect the location of our mean, median, and mode. We already saw a positively skewed curve on our example slide. So I always found it really, really difficult to tell the difference between positives and negatives. But the way that I remember it now is that you think about starting with your normal curve, symmetrical and in the middle. And then if you add an outlier very, very far away in either sort of the positive direction to the right or in the negative direction to the left, it's going to drag that curve just a little bit to point towards that outlier. So in our positively skewed graph, we have that extra long tail pointing out to the right. And that means there's some extra data points that are out on the right, and they've pulled the data in that direction. They've pulled that curve in that direction. And so we saw that our mode is completely unaffected by that pull, but the mean is very strongly affected by those outliers. So the mean gets pulled in the positive direction, and then the median stays, again, kind of in the middle. And then if we want to look at the same thing for negative, instead of having those outliers on the right-hand side in the positive direction, they're going to be on the left-hand side in the negative direction. Now, that doesn't mean that it's always going to be negative. It's just that it's pointing towards the negative. So don't get too caught up on what the value is on our x. Even if those outliers are still not below 0, they still count as being negative outliers if they're on the left-hand side of your main data. And again, we see that our mean has been pulled to the left, away from where the mode is. The mode doesn't move because that's the one that occurs most often and that isn't affected by those outliers. All right, so these are kind of the three big kinds of data you're going to see, and we can describe it as normally distributed. That's our ideal. That's what we expect in most situations. That's hopefully what we get most of the time. But we can have positive and negative skewed data, and that's usually just driven by some outliers. And if you get into statistics, you can do different things with outliers, whether they're mistakes or real problems, you can evaluate that. But this sort of discussion of these graphs and that distribution sets us up really nicely to start transitioning into those inferential statistics, where we can start making judgments using data. So if you've heard anything about statistics, you've probably heard the 5% rule. So you've probably heard a P of 0.05 is significant. That's that 5% rule. And the simplest way to state that is if the probability of an event is less than 5%, we call that a rare event, and therefore it is probably significant. So what that basically means is that if we have a probability distribution here, so in this case it's it's going to interpret it as what's the likelihood of each of these events occurring. So maybe we're looking at a coin toss. We're going to toss a coin 100 times, and we're going to get 95 heads and only 5 tails. That's a pretty big deviation from what we would expect. Our expected value right in the middle should be 50-50. So we're going to use that judgment of if the odds of that happening by pure chance alone, if we can calculate out what are the odds of flipping a coin that many times and getting that strange distribution of data, if it's less than 5%, then it probably didn't happen due to chance. So if we're saying that it's so rare that it can only naturally occur 5% of the time, it's probably being driven by something. So that's why when we're making conclusions, if we get that p that's less than 0.05, that's a probability value, more or less, we're saying that it's very unlikely to have occurred on its own, and so we're going to make that conclusion that it's occurred because of the manipulation that we've done in our experiment. Now that is a very simplified version. Again, if you've taken statistics, this might be way too simple for you, but that's, again, sort of as much as we need for this course, so I keep it fairly basic. All right, so the next thing that we want to consider is correlations. Now, correlations can be used in experimental research in special situations. Mostly, we're going to actually see correlations used in descriptive research, some of the earlier methods that we talked about, where instead of manipulating an independent variable and seeing how a dependent variable changes, we would look at measures of two different variables and see if they vary together over time. So we talked about there are certain things that you can't experimentally manipulate. Things like how much nutrition children get. But maybe you can look at something that might correlate with that. Maybe you want to look at household income or, I don't know, some other kind of measure like that you could then relate to how they grew up or intake in calories or something like that. So correlations are how we kind of make some interpretation of the association between two or more of those measured variables. We look at two variables because that's easier to visualize, because then you can have a graph that has one variable on the y-axis and one on the x, and look at it that way. But if you get into multivariate research, you can do dozens, and that gets really, really complicated, so we won't be doing that. And the one big thing that we want to keep in mind here is that we're finding relationships between variables, but we can't get enough information to infer causality between those variables. We can say that the thing on the x-axis and the thing on the y-axis are related. They seem to vary together very closely, but we can't say that x causes y or y causes x. We can't do that unless we can do manipulations. And so when we talk about correlations, we can actually quantify it. And correlation is going to talk about the direction and the strength of the relationship between two variables. So for our graphs here, the first one looks at studying on our x-axis and performance, their grade, on the y-axis. And if you logically think about those two things, we might assume that they are positively correlated. As you study more, your grade should improve. But, again, we don't want to make causal statements. We might say also that those who have higher grades might study more to maintain those grades. We don't know which direction that's going in. So our statement would be that there's a positive correlation from this data here that between studying and performance. So as one increases, so too does the other. We might look at our middle graph, and that's looking at our grade again on that y-axis, but this time we have absenteeism, or number of days missed, on the x-axis. So here, they're showing a negative correlation. So instead of both increasing together, as one goes up, the other goes down. So those with higher grades miss fewer days, or those who miss more days have lower grades. Again, we could infer a little bit what direction that probably goes, but we can't be positive until we test it. So there's a negative correlation there. And then in our last graph, we're back to studying and performance, but this time instead of our data sitting nice and close to that line, it's a little bit more spread out. So we still have a positive correlation between those two traits, between studying and grade, but this time the data is more spread out, so it's not as strong of a relationship. And because these are probably new ideas, I actually go through this a couple of times with different visuals. So if it hasn't sunk in yet, not to worry, we're going to go through it a couple more times. If you already understand correlation coefficients, you can zone out for the next 5 minutes or so. All right, so the correlation coefficient are actually the number that we use to talk about those correlations. It is sometimes also noted as R, and this describes the relationship between the two variables that we're interested in. So R is going to range between -1 and +1, so that's the scale at the bottom. -1 on the left, +1 on the right, 0 in the middle. So R can fall anywhere on that scale. And that's going to give us two different very important pieces of information. The first is the sign. We can have a positive or a negative correlation. And just like we saw on the previous slide, we can have sort of a positive or a negative relationship between our variables. So that's what this number is going to mean. So if we have a negative correlation, that means that as one score increases, the other decreases. If it's positive, they both increase together. And then our absolute value, how close our number is to 1, is going to tell us the strength. So 0 is not very strong, and 1, whether it's positive or negative, is very strong. So the positive and the negative tells us one thing, and then the size of the number tells us another. And we kind of have to look at them both separately. So if we want to break it down, again, into the basics, our positive correlations is anything to the right of 0. So anything larger than 0. This is saying that an increase in one variable is related to an increase in the other variable. The more that you study, the higher your grade. Or the higher you grade, the more that you study. So anywhere between or just above 0, all the way up to or equal to a +1. Negative correlations are the other side on the left of the 0. An increase in one variable relates to a decrease in the other. So the more you miss school, the lower your grade. And again, we can state it either way. And so that's going to be between -1 and all the way up to, but not including 0. And as I said, 0 means that there is no relationship, positive or negative. At lowest strength, there is no association between our two variables. They are not correlated with one another. And so we can make some decisions as to how close to 0 we let that R get before we say there's no relationship. It again depends on what you're looking at and other factors. But when we're looking at stuff for this class, we'll keep it pretty clear cut. So we have some extra examples, some visuals of a positive correlation. So if one variable gets larger, the other also gets larger. In the middle, we have what 0 correlations would look like, where it's kind of messy and scattered. There's no way to draw a line that runs through the middle of that data that is the best way to describe it. If you do statistics, you might have heard of like the line of best fit. So for the first graph, you can draw a nice straight line right down the middle of those points, and it fits really nicely. But our 0 correlation, you could draw the line vertically, horizontally, at an angle, the opposite angle, and they're all about the same, which tells us that there's no perfect relationship, there's no way to correlate those variables. And the last one is a negative correlation. So again, as one increases, the other decreases. Now this is something really important to note, because a lot of people sort of misinterpret the negative correlations, and they might say that both, as one gets more negative, the other also gets more negative, but that's actually a positive correlation, because let's just look at it as this scores lower, this one scores lower. So if your directions match, as one gets bigger, the other gets bigger, or as one gets smaller, the other gets smaller, if they match, they're positive. If they are opposites, they're negative. And that's sort of the big hint that this is something that I will almost always ask on an exam. And of course, we can have somewhere right in the middle. And if I go back to our first graph, this should give you a better idea of that last graph there, where the points are more spread out. That would be a positive correlation, so a plus in front of our R. But looking at it, it would probably be an R of 0.5, maybe 0.4. So not very strong, but also not zero. So we would consider things like the direction separate, and then the magnitude as how close together those data points are.
It could have been a zero correlation also. Right.
Not on this one, though, because there is that way to draw that line. If we can draw a line to it that is sort of fitting the data, then it's just going to be a lower R, but not a zero. If you get like a perfect circle of data where there's no way to draw a line, then it's a zero. Yeah, and usually what I'll do for questions is I'll give you either a couple of R values and say which one is the biggest, or which ones are negative, or which ones are positive, and ask you to sort of tell me, like, what is the strongest association or the weakest or whatever. And you just have to know positive and negative for direction, and magnitude tells you strength. Those are the keys. All right. And so we might want to think about the advantages and disadvantages of correlational research. So if we want to run correlations on two or more measured variables, when is that good and when is it bad? So some of the advantages here are that it can show the strength of present relationships. We can measure two variables of interest and see if they're related, which can be very useful, especially if you're looking to set up, say, future experiments. And you would like to see just from existing databases, is this something that could be related? It's a good place to start. It's also a great way to make predictions about variables. So we can measure things like level of CO2 in the atmosphere over time. But maybe we haven't been measuring it far enough back. Maybe we've only been taking sort of accurate scientific measurements as long as we can. And before that, we have to guess. Well, if we've done a good correlation and we have all of this data where it's been accurately measured, we can kind of draw that line backwards and make some assumptions to get a fairly accurate prediction backwards. We can also predict into the future for similar logic. So if you have good data in the middle, you can make some assumptions and project forward and back. And you can also do that if you're trying to find for, I don't know, maybe you only measured people who were between these particular ages, but you want to guess what you would have for someone who's a little bit older or a little bit younger, or something like that. So you can kind of fill in the gaps in your research using your prediction from that setup. And again, this helps us identify the potential for real-world associations. Is X related to Y? A lot of times, if you want to run an experiment and you have no idea where to start, you'll start by doing very large multivariate correlations and see if any variables tend to correlate with your thing of interest. So if you're interested in how much songbirds sing, then maybe you're going to look at values for absolutely everything you have available to you. Maybe you're going to look at hours of sunlight, how much rain, or traffic density, or population density. And you're going to see if any of those vary in the same way that your songbirds do. And then that would be a good place to start an experiment if you find any that are associated. So you can do all sorts of stuff this way and test as many variables as you can get your hands on to see which ones might be related. Of course, for our disadvantages, we still have that inability to assume a cause and effect relationship. Even though logically it seems like we could probably figure it out, in a lot of cases there are other things that might be going on. So like I said with the studying and grade, that people who have higher grades might be more motivated to study to maintain those grades. We'd have to be able to maybe measure what is motivating them to be studying. if we wanted to make sure that it was just the act of studying that was causing higher grades, and it wasn't sort of a both at once kind of a thing. We have to keep in mind that, so relationships may be due to a third unmeasured variable, so there could be something else going on. One of my favorite examples of this is that you can look at graphs that show a very strong correlation between the number of ice cream cones sold per capita and the number of shark attacks per capita. The really nice positive correlation. As more ice cream cones are sold, there are more shark attacks. But we're not saying that eating ice cream causes shark attacks. There's a third variable that explains it, which would be outside temperature. As it comes into summer, there's more ice cream sold. There's also more people at the beach, so more shark attacks. So that's one fairly obvious example, but those third variables, those extra confounding variables, can be floating around in the background. And with correlational data, we can never be positive that we've actually controlled for all of them. So we can try and measure as many things as possible and pull things out statistically, but this is one of the major reasons why we try not to make causal statements with correlational data. So we show an association, not a cause. And again, if you do more statistics classes, there are ways that you can jump through the right number of hoops to start making some correlational claims, causal claims with correlations, but it's a very touchy subject. And this was another example of things that could be misleading. So if we looked at intelligence and birth order, the correlation between those, we might look at that and assume that the firstborn children are smarter and children born later are less intelligent. Or we could consider the fact that if the researchers haven't controlled for age, then those who were born earlier are older and have more experience and would therefore test higher on an IQ score. So there are extra variables that always need to be considered. So correlations can be very misleading, and you need to be critical about what else might be driving this relationship. So we just want to think and be aware of other stuff that's happening in the background. All right. So the next thing that we're going to start talking about is basically stuff that we want to watch out for. And a lot of these we've kind of talked about already, but this is putting them all together in one place. So when we're evaluating research, when we try and decide, is our result something that we trust? Is this a good study? Is this something that we can apply elsewhere? We want to start considering all of these things. So the first thing is sampling bias. So when a sample isn't actually representative of our population. So if we only talk or interview a subset of our population, and that subset isn't the same makeup as the larger population, that's problematic. One of the best examples I've seen of this was on Twitter, and somebody had done a poll on Twitter that asked, do you use Twitter? Yes or no? And obviously, that is a biased sample because in order to see it, you have to be on Twitter. But that was part of their argument about where you choose to advertise or where you choose to get people to answer your questions. That can be problematic. And there's older examples of this where they've mailed out surveys that ask if people respond to mailing surveys. And of course, like 97% of people that responded said yes. So again, very biased data. So we need to keep those things in mind of how did they get the sample and was that the best way to do it? Is that sample representative of the population we're interested in? The next thing is placebo effect. So we'll talk about that where people's expectations can influence what they experience. So if they think that they're in the experimental group and that this drug should make them feel better, they might start feeling better just due to the psychological expectation. And that's why a good design, a good setup for research is to actually control what they expect. So if the control group and the experimental group are treated exactly the same, they don't know which they're in, and then any difference between those two groups has to be due to the drug or lack of drug as opposed to expectation. We also want to keep in mind our distortions in self-reported data. So that social desirability bias, where you want to make yourself look good. You want to make sure that you answer in a way that doesn't make you look bad. We also have a response set. I don't think we gave a proper name to this one when we talked about it, but this is like when you're doing surveys and you sort of respond either right down the middle, you don't want to commit to either side, or maybe you're just really bored and want to get this over with, so you strongly agree or strongly disagree with absolutely everything. So a response set is that tendency to respond to the questions in a particular way. So those are the three things that you typically see as middle of the road, making no committal statements, or one extreme or the other. That's the usual. And this is, again, a little bit beyond the scope of the class, but the way that we get around that as researchers is that you tend to ask the same questions multiple times, but framed different ways. So we might frame it as ice cream is better than pie, strongly agree or strongly disagree. And then we'd ask it again later on and say pie is better than ice cream. And if you're answering properly, you should switch your response. But if you're using a response set, you will strongly agree with everything, even statements that contradict one another. So that's sort of the secret behind the scenes on how that works. We also have a halo effect, which is a tendency to let your initial performance or what you thought at the beginning influence your future perceptions. This is a really interesting one, and there are some really cool studies where if you're paid to do a task, and then they continue paying you to tell other people that the task is really fun and that they should do it too, and if they're getting money for every time they tell you it was great and other people join, people will change how they view the task. Even if it was really boring, because they're telling other people it was cool, and they're not bad people, it must have been cooler than they remembered, and so they change their perception, which is just really neat. We also have our experimenter bias. We mentioned that, where our experimenter can interpret neutral data, usually that's interpreted towards the supporting of the hypothesis they want. And it's not always intentional, though in wording it seems intentional, but it's just something where humans tend to be easily biased. And so to try and counteract that, we can use a double-blind solution. And that can actually be kind of like our solution to the placebo effects as well. When both the experimenter and the subject have no idea who's in the control group and who's in the comparison group, the control group for the experimental group, then nobody can be biased in either way. So that's one of the best solutions to get around both of those problems. All right, and then the last thing, we have a couple of minutes here. 3 slides on ethics. Now, I always give a little bit of a disclaimer here that you can take an entire course on ethics in science. This is one of those really big topics that you can talk about ad nauseum. But because of the scope of this class, we kind of give you an idea of what information is out there and the basics of it, with the assumption that if you want to know more about it, you can look more into it, but we keep it kind of basic again. So you might already know, but ethics is basically the set of general principles of how people should be educated, treated, and respected when participating in a study. So it's obviously geared towards ethics or psychological research. And most of what we see, especially in our textbook, is going to focus in on human ethics, or how you work with participants. There is a whole other set of rules that is equally strict for dealing with animal subjects. So I'm actually a lot more familiar with that set of ethics due to experience, but a lot of the same rules, at least in spirit, can be applied to both sets. All right. So the general principles, the general ethical principles, they focus on 5 basic principles. And I just wanted to, I'm going to scroll down my notes here. All right. So these are basically set up and governed by internal review boards, called IRBs. And every university that conducts research, every association that has members that conduct research, they'll all have their own internal review boards. There are also ethical review boards for journals that look such papers. So you can't work anywhere, you can't publish anywhere, you can't get approval for research unless you meet all these ethical principles. So we can focus on beneficence and non-malfeasance, which are just the worst ways of saying it. You want to make sure that you're... Oh, I thought I had my notes that match that. Okay, apparently not. Maybe I'll leave it there and come back to each of these in detail, because I'm trying to remember how I match my notes and I don't. And we're real close, so I can't stumble through it. But I will finish this slide on Wednesday and make sure I get it right. But yeah, have a good day, or afternoon, or whatever it is.